The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Well, I must say that what Ramon said, most everything was absolutely correct. And that's something that has changed, though. Everything he was saying about constructability has to be constructible. We want durability. A lot of specs call for durability, but it has to be constructible. We have to work with material, mechanical properties, structural properties as well. So all these have to be in balance. And typically in the objectives of construction, you're always balancing cost and performance. It's a typical motto for engineers, is to balance that. But it's changed a bit. The owner will say, I want 125-year service life. I don't want to tell you I want 5,000 PSI. So what's really been the big change is engineering community, the contracting community, used to see specs that called out for at least 5,000 PSI concrete. Now they're seeing something that's 125-year. How do you balance that? How do you bridge that gap? And that's what the whole field of service life engineering has come about because of that. Now, another thing that's been a huge dynamic is now 51% of all contract vehicles are design build. Design build and operate is making a large change in the way the construction industry conducts its business. We'll hear from Kiewit and the like. That's a main bloodstream for the contracting community is design build now. Because it's design build, the engineer and contractor team up. And that's a big change from the design bid build world where you have a lot of this conflict, finger pointing. What's good about the new world of design build and design build operate is the fact that you can actually do service life engineering in conjunction with each other to make sure you have your constructability issues and your strength issues and your durability issues to meet the specifications. An example of some projects that are currently underway that are requiring service life engineering, the St. Lawrence Bridge crossing in Montreal. I must say that it would be nice when they name it because it's all called New Bridge over St. Lawrence. But this bridge has a 125-year service life. It's fast track, has to be built in 2 years. So it's a very, very aggressive attack. This is a design, build, and operate, where the design and construction team design it, build it in conjunction with the maintenance programs from the operator, and then the owner, country of Canada, wants to know what the condition of that structure will be at 30 years. They also have some milestones for many different elements. Some are replaceable and some are not. So there's a very complex world with the service life engineering where they're calling out for years, but they're not always the same 125 years. But the contractor and engineer can now team up and look at all the materials available and means available to do this at the lowest cost. This was St. Lawrence Bridge crossing. This is Lavalin and T.Y. Lin and IVT, main teams. The Goethals Bridge in New York City. This is a $1.2 billion project, one of the first major design, build, and operate contracts from the New York, New Jersey Port Authority. The structure here has 125-year service life as well. Most of the main elements on this bridge is 125 years. This one's we're working with Kiewit on this project. The K Bridge in New York City, the same way, 125-year service life. And Tappan Z Bridge. These are all monumental bridges in the U.S., and this is not all of them. There's at least another dozen structures that all have the specification for service life requirements. How do you get there? What it is it's a team. Every one of these are a design-build project. So when you have design-build projects, you can actually look at what the owner's looking for and do so in a constructible way that has the strength and aesthetics that you're looking for. A couple case studies that we did. I picked two of them. This is the Pier 5 project in Norfolk, Virginia. It's set up so you can have 2 aircraft carriers on service at the same time. Owner is the Navy. It is a pier. And What they're requiring on this one is a 75-year service life. Case 2, this is that bridge across the St. Lawrence. That's a 125-year service life. And the owner is the country of Canada and not Quebec. On the first case, the project requirements, when you had to put a submittal together, the example case 1 is an example where the design build team puts together the materials, the submittals, all the test materials that are needed to submit into a durability plan to the Navy. So that's what happened, where they put all the requirements there. The mixed design was submitted. The internal laboratory testing, where this is internal to the design build team. The service life modeling to justify their design. And also each concrete element and mix would have its own specific quality control plan. Now, some things that the project had requirements on was service life, and they defined that as the corrosion initiation plus the propagation period, which was about 10 years in the specification. They wanted 75 years to be met. What they did was to try to eliminate some of the guesswork and some of the variability that could occur. The Navy set a lot of the boundary conditions for the modeling itself: temperature, humidity, exposure conditions by element. So they put that together within the specification itself. The submittal package would then have your durability requirements by the element, the mixed design submittal, the concrete mix testing, service life modeling, and then the quality control plan. The mixed design would have the typical mixed design you would have: the proportions, the material sources, the concrete properties, the historical performance, the cement mill certs, and the like. The laboratory testing on service life engineering is a little different. What you'd have is the laboratory on transport properties, how things come into concrete and how they come out. So the porosity, the ion diffusion coefficient, and the moisture diffusion coefficient. Essentially, porosity tells you the number of available voids. The ion diffusion, how tortuous are those void systems? And then the moisture is, how does water move in and out? So what you would have is, you would have a mix, and in the case of the Navy, they wanted a mock-up put together as well as laboratory mixes. So you would have cylinders and cores, and you would have the test results from those so that we can use those going forward into a quality control program. The data itself would be modeled where you would have predicted chloride content, duration in years, and then eventually critical levels of chloride that would cause corrosion, whether it's do nothing with the black steel, or if you would use galvanized or different levels of corrosion inhibitors, you'd have an extension. So as time goes on, you'll see that at this concrete cover, predicted chlorides without any protection means would not make the 75 years. However, putting in a protection system, a calcium nitride or a different type of reinforcing, will definitely get you with the propagation time that amount on a deterministic basis. Now, when you establish your quality control program, if you know your limits on your properties, then you conduct a lab to check the compliance of that. If the IDC test data is below requirements, it's acceptable. The lower the number, the better. Higher than that, it would go into modeling itself. Let's take that value. In and itself, that one value doesn't say yes or no. So what you want to do is then model it, see if it meets those and it's acceptable or not. When you do enough of these and you have a project that has enough of it, you can develop a curve in which you have your one parameter and the other parameter and the relationship of acceptance and rejection, the combination of the two major elements. You can build a curve so that when you have the data coming in from the field, you can start looking at this and seeing where they comply. If you have points that are outside, these are the ones that may have one number is high but the other number is low. What you want to do is run that, see if it has an effect. The nice benefit of having that type of an option, if let's say this outlier here had a problem, you have that modeling and you have the prediction of that time. Now you can apply repair or protection systems for fixing that area of a structure if necessary. Now, the second project, the St. Lawrence Bridge project, this was chosen as different. Sometimes the engineer, contractor, design build team want to have full control over everything. On other cases, the design build team would like to work on the project but have other manufacturers or material suppliers be on the hook to provide some level of performance themselves. So in the case here, the ready mix producers and the precast operations had to provide a lot of their own quality control testing on their product. So in a submittal process here, you would have the project define the durability requirements established in the corrosion plan, the modeling prediction of what needs to have from the material suppliers. The mixed designs would be submitted. It's not an RFI, but it would be a submittal. External pre-qualification testing would be provided in that submittal, and then the external quality control program would have to be put in place too. They're periodic, I think in the project for St. Lawrence, it's about every 250 cubic meters. They have to run the performance on that mix. So what they would do in this case would be provide a family of mixes. The producers would come in and run testing on a different level of binary and ternary systems so that they can handle a family of applications on the project. And then their data would come in, and then also this data is tested according to some other rather quick test methods, rapid chloride permeability and more common tests, so that they could actually be correlated together. Now the pre-qualification testing would be, they need to provide the data on transport test on each of the mix. The rapid chloride permeability, so we can have further future correlation of the transport test and also the RCP test. Then the compressive strengths, the freeze thaw, the scaling, a lot of the tests that you want to have to prevent cracks, like the shrinkage issues and the like. The designer and the contractor together tend to team up pretty well to try to eliminate cracking as much as possible. It doesn't do anybody in that team any good if they did. So they try to do their best to minimize that and use the right materials to have the other durability concerns taken care of. The pre-qualification testing does get a little bit more involved when you have transport tests. Beginning the testing, you get a 28-day test, you get a 28-day accelerated test, and what you get is a rough idea, but it's a data point. Then, as was mentioned, we'd like to see the rapid chloride permeability test as well as the other transport test, the stadium-based testing, run at 90 days and 90 days accelerated so that you can pick some points and have a good data and a maturity curve for that concrete itself. Now, if it meets it, everything's fine, great. Now, sometimes the concrete itself doesn't have to be the solution for the durability. Sometimes you add other systems. You might have the reinforcing, might be instead of black steel, you want to use a galvanized or an epoxy coating or a stainless steel. Then you might add surface treatments. You might have coatings. You might have other things that you can apply. So the concrete itself doesn't have to meet it, but the whole package together does. But in the situation here in St. Lawrence, the concrete portion had its own performance limit that they had to have because they were considering the different types of reinforcing and other types of surface treatments as well. So what we did was then you can do the rapid chloride permeability and the IDC and develop correlations with the different time periods of maturity, building a curve so that then at a future time you can do these tests more rapidly and be able to say, are you on the right track or not? And again, I fully agree with Ramon. The best way on this RCP is to do it at the regular 28-day, but also with the accelerated 7 days of normal moist curing at 73 degrees, and then 21 days of accelerated at 100 degrees. This is something very typical of what Virginia would be doing, DOT. And then in this project, the testing itself would go off into third-party laboratories. I think there's laboratories up in Quebec and others that would be running tests. And those limits would be coming down both in RCP as well as in some transport tests periodically. And then if there's any problems, you can model it. If there's any issues, you can also then come up with a solution with the type of other protection systems to add to that area of the structure. So what we had here is a presentation that's based on the fact that this is being done. The fact that design build and operate contracts are out there. This is a perfect venue to put in service life engineering. The team itself wants success, and the owner can actually ask for years and get that delivered to them.